Mindsetters, Matrix, it is finally your time to learn more and learn extra with Looney and Phil again. Phil, how are you doing?
I'm great, thanks, and you, Looney?
I'm good, thank you. What are we doing today?
We're talking about some cells and some batteries today, so hopefully these guys have charged up their batteries. We're going to get going.
That's cool. Mindsetters, you're doing cells and batteries. That used to be my favorite section in physical science once upon a time. I hope you guys are ready to learn, and I hope you are hitting us up on Facebook and Twitter. It's been very quiet on Twitter. I hope you know our address is at Learn Extra. That's our Twitter handle. Facebook, it's facebook.com/Learn Extra. Remember to download the show notes, the videos, the schedules on Learn Extra, co.za/live. Remember, I do post all the notes on our Facebook page, guys. I try to copy and paste as much as I can from the notes as well to give you guys the extra information. So do make sure that you keep your eyes glued onto our Facebook page. Thank you to Macmillan for bringing us this great show. I will tell you about the Stars in Education Awards later on in the show, but for now, let's get back to Phil.
Okay, well, grade 12s, it's nearly the end. I want you guys to hold on tight. You guys are probably writing your prelims fairly soon, or if you haven't written yet, I hope that you're studying really hard. Guys, this is the final stretch. Your teachers should be finalizing all of their theory. For most of you guys, this should just be a little piece of revision, and I'm hoping that we can help you out today and start to talk about some cells and some batteries, and hopefully you learn some things along the way. So what I'm going to be doing is I'm going to be taking you through the theory behind cells and batteries. We're going to take a look at some exam-style questions right at the end. As Looney says, get on the page, get the notes, get the videos from especially the electrochemical cells. That was very useful, and for E0 cell calculations. Guys, I'm going to be doing a little bit of redox revision. But before I say too much, let's put the menu up on the screen. Let's show you exactly what's coming your way today. Okay, so what we're going to do is we're going to talk about how cells actually work. And we're going to start investigating spontaneous reactions that produce energy. Okay, so we're going to talk about the energy which comes from cells. And that's something that I really like. I'm sure most of you have dealt with something with flat batteries before. I'm sure you've said to somebody, my batteries are flat. Okay, so we know that batteries have got something to do with energy, and we're going to be talking about the cells inside those batteries. And I'm sure that you all know about the remote battery, and you can talk about your cell phone battery. We're going to take a look inside those. And then in the very last section of today's show, we're actually going to show you a battery that I've built myself. Okay, now we're going to identify the parts of a cell. Guys, please, identifying the parts of a cell, let me not cross that out. So identifying parts of a cell is really, really important. Guys, you've got to know what an anode, a cathode, an electrolyte, an external circuit all looks like, and be able to label it yourself. And more importantly, not just learning diagrams, I need to know what each part does inside a cell. And then, here we go, we're going to calculate the amount of charge and energy which is stored inside a cell. And that's what I'm really concerned about, because a lot of people are not familiar with these formulae. So the amount of charge is really important, and then obviously the energy which is stored inside a cell. The reason that we're going to be doing this today is because, guys, there's some really weird units that appear on batteries, and I want to show you how to work with them. Okay. Now, to distinguish between primary and secondary cells, I've actually got a primary cell and a secondary cell. The secondary cell I built myself, as I said earlier. And in the last section of the show, I'm actually going to show you what that secondary cell does, how it looks, and I'm actually going to show you that we can put energy into and take it out again. Okay, but before we get too carried away, let's get into our show. Okay, now let's start talking about where these batteries actually come from and what sort of theory we need to know before we go anywhere. So here we go. Now, this is something across the board, whether or not you're talking about a cell phone or a TV remote or inside a torch battery, whatever the batteries are, and even the battery on my microphone here inside the studio is powered by some batteries. Now, sometimes I get this word batteries and cells confused. Just to make sure that you know the difference, many cells make up one battery. So when I talk about a cell, that's one individual thing. I've actually got a cell over here. Guys, this is not actually a battery. This is one cell. Now, we're going to take a look and see what's inside a cell, and we're going to try and figure out how I get my energy out of here. This 1,5 volt cell. Now, this is called Duracell for a reason. It's got the duration to last. Now, this one cell, many cells can make up a battery. So, guys, again, this is not a battery. This is a cell. Okay, so you can correct all your family members that call this a battery. This is not called a battery. It's a cell. Okay, now we're going to deal with the energy which comes out of those cells. Now, to do this, and I know that this is a part that a lot of people kind of cringe and they're a little bit afraid of, but guys, again, I'm going to hold your hand. It's all to do with redox. It's all to do with reduction and oxidation. Okay, so now let's just do a little bit of background. Why am I talking about redox? I thought I was talking about cells and batteries and all of that. Okay, now here's where this goes. Now I'm going to spell it out beautifully why we need to take a look at redox when we're taking a look at electrochemical cells like the one that I just showed you. Here it goes. Now, redox reactions. Now, I've got to remind myself what redox reaction actually, what's actually going on inside one of these cells. Okay, so now here we go. One chemical loses electrons. Now, I don't particularly like that word lose because I lose a lot of things, and that usually means that I never see them again and they're gone. Now, when something loses electrons, I'd rather say that it gives it away. But loses electrons works very well with that analogy of oil rig. Oxidation is loss, reduction is gain. I'm sure that you've seen that before. So we're going to talk about oxidation is loss, reduction is gain, if you didn't know what oil rig stood for. Okay, but then, this is why I say that it's not lost. One chemical gives away electrons. It loses these electrons. And one chemical likes to gain electrons. So here's the story. One chemical doesn't really like its electrons so much and decides to give them up. Another chemical says, give me those electrons. I want those electrons so badly. I will do anything for those electrons. Now, here's the thing. I see an opportunity over here. Let's make the electrons work along the way. Now, that's really where cells actually come in. When you put a battery or a cell inside something, what you're doing is you're saying to these two chemicals, I'll give you what you want, but you've got to do something for me in return. You have to turn on my torch. You have to turn on my cell phone or my TV remote. Anytime you're making a cell do work, I'm saying to the one chemical that wants to give away its electrons, I'm going to say, no, you can't give them up yet. I haven't plugged you in. What you do by plugging them in or attaching or switching on is I'm allowing these electrons to move from one chemical to another chemical. And it's as simple as that. One chemical wants them, one chemical doesn't have them, and it's going to grab those electrons any way that it can. Now, what happens is, as it switches on my cell phone or as it switches on my TV remote, is I'm allowing those moving electrons to do some work. And that's where that energy actually comes from. Okay, so now that we've established the idea that there's some redox going on, we're going to start dealing with some chemicals. And later on in the show, I actually want to start dealing with this. Now, guys, this is a bit of a challenge for you. You guys can actually make your own battery. You can actually make up your own cells as well. All you're going to need is two different metals. I've chosen zinc and copper, and I'm going to show you that a little bit later on, and some sort of acid. You can do this with some vinegar if you like. Now, what I can do is I'm going to be using some sulfuric acid a little bit later on in the show, in the second segment, and we're actually going to make a cell. I'm just going to reach over here. I'm going to talk about these plates. Here we go. All you're going to need is two metals with some exposed metal. Now, you can use any two different metals. I advise that you use something with copper inside it. I'm sure that there's some screws lying around inside the house, or there's some old keys which have got sort of a brown color, which means that they've got copper inside. Okay, you just need two different metals and some sort of acid. Now, lemon juice will work, vinegar will work. And the really nice thing about this is if you put enough of these together, you can actually get some useful energy out of these. And I'm going to be doing a bit of a demonstration after our first ad break, and then we're going to see how much energy I can actually get out of something with two metals and then some sort of acid. Okay, but now, before I get too tied up in the actual demonstration, what I'm going to do is I'm going to show you how to start dealing with this in a grown-up, adult, grade 12 redox way. Now, a lot of you see this table down at the bottom of my screen, and you're kind of like getting unhappy and uncomfortable in your seats. But guys, once again, I love holding your hands and helping you through this. Guys, redox really doesn't need to be difficult. I'm going to take you through the first steps. We're going to find out the reactions together, and we're going to see what goes on. Okay, so I've got copper metal. So what I do is I identify the chemicals which I have. I call them species. Just like animals out inside the zoo, I call them species. Different metals are different species. I have got a copper metal species, I've got a zinc metal species, hydrogen ions, and sulfate ions. Okay, those parts came out of my sulfuric acid, if you're wondering where those came from. Now, that's the first part. I know that there's no sulfuric acid. There is no H2SO4 on this table, so I need to split it up into ions. Now what I'm going to do is I'm going to find the species on the table and circle them. How you do this is going to decide whether or not you're successful at using your table correctly. So what I'm going to do is I'm going to turn my attention to this table. I've highlighted only the piece which has got the chemicals which I need. I'm going to show you how to work with this. And guys, you can actually do this with your metals at home. If you know what metals you're dealing with, really nice. Actually just reach into your wallet. I'm hoping there's a few coins. Now brown coins and silver coins are made of different metals. If you do a little bit of research, it's mostly nickel and copper inside there. Now copper and nickel can actually make an electrode potential, and if you stack enough of them on together using some cardboard, I can actually show you how to make a beautiful electricity battery out of those. Really not too difficult. Okay, but before we get too sidetracked and you're busy building all these amazing contraptions inside your mind, let's deal with some of the species which I've got. I said to you that I have zinc metal inside this potential cell that we're going to make later on in the show. Now, I do not have zinc ions yet. I don't have zinc 2+. But what I do have is I've got some copper on my hands. So let's go down a little bit and let's circle the copper metal. I know that I have copper metal. You can see that these are two metals on opposite ends of my redox table over here. Now, here's a little bit of a hint. If you want to make lots of electricity, choose metals which are very far away from each other, and you're going to get more voltage. I wonder if you can think about the reason why the further away they are produces more voltage. So that's a little bit of a challenge. Maybe you can answer that for me on the Facebook page. Okay, what else do I have? There's several other species involved here. I've got hydrogen ions over there, right? And there's all sorts of things going on here. I've got hydrogen ions over there, and then down at the bottom here, there's sulfate and hydrogen ions together. But now there's one particular problem with this. This sulfate requires really high concentration of H+ ions. I'm going to use dilute acid. So what I'm actually going to do is I'm going to make this reaction out of bounds because that reaction is reserved for concentrated sulfuric acid. The reason that I know that is because of the really high concentration of H+ ions. Now what I'm going to be doing now is I'm going to try and predict what the reactions are going to be. Now remember what I said, you've got to choose the best reactions for the job. Now, how do I do that? How do I know? I don't know zinc personally. I can't ask it questions. What I need to do is I need to make a choice based on information which I have. Now, lucky for us, on the side of all the redox tables, I've actually got arrows to tell me which one to choose. So on the left-hand side, I've actually only really got one choice, and that is H+ ions. Doesn't matter which type of H+ you've got, if it's vinegar. If you were watching the Grade 11 show, we talked about vinegar, we talked about acetic acid, we talked about hydrochloric acid and a couple of others as well. H+ is a result of an acid. So it doesn't actually matter which acid, it all works. And this is one of the ways that you can actually make a battery out of a lemon. A lemon has got that H+. So I've got one reactant over there, which is H+. On the other side, however, I'm presented with a choice. Copper or zinc? Well, if I'm following my own advice, all I have to do is follow the arrows. Now, between copper and zinc, I'm going to choose zinc. And this is the way that I decide which one is going to react. Okay, now the only reason that that sulfate ion down at the bottom is out of bounds is, guys, this reaction is reserved for concentrated sulfuric acid, really concentrated sulfuric acid, and I don't actually have that. What I do have, however, is a very large amount of H+ ions. H+ is going to be reacting. So now, how do I decide my reactions? And I'm hoping that you can guess. What I'm going to do is I'm going to start with the ones that I've chosen. I'm going to start with zinc. I'm going to start with H+, and we're going to move across to the other side of the table. So we start off by writing our chosen reactants. And let's actually do that. Let's make some space down at the bottom. And I hope you guys are doing this as well. I'm going to start out by saying zinc. I'm going to start out by saying 2H+, because these are the ones that I've chosen. You always write down the ones that you've chosen as your strongest reagents. Then you move across to the other side of the table. So zinc starts on the right-hand side and moves across to become zinc 2+ plus 2 electrons. Now just remember when you write these out that it becomes a single-headed arrow because now we know which direction this is going. This is no longer reversible. So we've got zinc 2+ plus 2 electrons. What happened to our hydrogen? Our hydrogen, according to our reaction, let's take a look. Our hydrogen takes 2 electrons and turns into hydrogen gas. And we might actually be lucky enough to see that. So plus 2 electrons goes to make H2 as a gas. So what we should be seeing is at one electrode we should see the zinc disappearing, and at the other one we should see hydrogen gas as a formation. I'm hoping this happens, but guys, what I want you to do in the ad break is I want you, if you can, to try and figure out how much electricity I can expect from a cell like this under standard conditions. A real challenge. But guys, get on the Facebook page, get our notes, get sharing. Looney, how's it looking?
Well, Zova has a question. He says, our teacher almost told us to choose which have 2e electrons always, unless they specify. Is that the most accurate? Good idea.
It depends on what you have. There's not always 2 electrons.
Okay, cool.
Okay, so guys, be careful of shortcuts or rules which might lead you into always believing that something is correct. It's not always 2 electrons, because sometimes there's reactions with only 1 electron.
Okay, cool.
Be very, very careful, especially in redox.
Okay. Quick question from James. Electrons flow from the negative to the positive, right?
Oh, it depends. Okay.
Okay.
Right, if we're dealing with electrochemical cells, absolutely. From the negative point of a battery to the positive point of a battery, that is absolutely correct.
Okay, cool. Mindset is let's take a very short break. I will check out your answers your questions during the break. I'll ask Phil and then we'll get back straight after this. Welcome back, Mindsetters. If you've just joined us, you're with Looney and Phil, and we're going over cells and batteries. So, Phil, we have a question here from Maureen. She's asking, how will I know which copper to use, because there are many coppers on the table of standard reduction potentials?
Okay, that's a really, really good question. Okay, so Mindsetters, when you're taking a look at your standard reduction potentials, it looks like there's a copper plus and a copper 2 plus and a copper. Guys, you've got to be very careful. You've got to identify exactly what you have and circle everything that you have. Now, in our experiment, we only had Cu. So that means that I can only circle Cu. I can't circle Cu plus, I can't circle Cu2 plus. Guys, you don't have it. If you don't have the ion, don't circle it. But if you do, obviously go ahead and circle it and then follow through. Now, I want to get back to our experiments. Are there any other questions?
No, just that one.
Okay, right. So mindset is what I said was we were going to take some zinc, so 2 different metals. So over here, I've got copper on the left of your screen and zinc on the right of your screen. What I'm going to be doing is I'm going to be measuring the potential difference between them. I've got a beaker over here, which has got some dilute sulfuric acid on the inside, and hopefully we're going to get some voltage out of this. Now, it's just a very small demonstration of how to get voltage out of it. I've got a multimeter over here which can measure very, very small voltages. You can actually see that there's very tiny voltages even from moving around the cables. And what I'm going to do is I'm going to apply my electrodes to see what voltage actually comes off here. So now, what I know from my reactions is that zinc should be oxidized. Zinc should be giving away electrons. Now, that should give you a little bit of a clue as to which side is negative, and I want to see if that's true. So guys, I said that zinc is giving away electrons. Oxidation is taking place at this zinc electrode. Now you'll notice that I've picked up the black electrode. Now the black electrode is usually the one that measures the negative side of a battery. Now you can see on the other side that I've picked up a positive, so hopefully I'm going to get positive on the other side with the copper. So what you'll see if there's a positive voltage is the voltage will be read out on the screen over here. So what I can do, there we go. Really, really nice. You can actually measure the voltage. Around about 0.96 volts, which are coming from this battery. And I'm not sure if it's a little bit too close to actually see, but you can actually start to see there's some bubbles actually starting to form from the surface of my copper over here. And one of the really nice things that you can see as well is that reaction at the surface of the copper has actually cleaned my copper really nicely. This electrochemical reaction is one of the ways that, that metals are cleaned. I haven't actually eaten away the copper, but what's actually happened is that reduction has happened over the surface over here. And I'm going to put this back in here and try and see if we can't get some of the bubbles. I'm actually going to turn this to measure some current, and we're going to try and see if we can't get some bubbles going in there. Right, so what I'm going to do is I'm going to switch this on to measure some current, and hopefully we actually get some really nice current flowing there. Right, I'm actually starting to see some really nice current flowing there. And there's some very, very tiny bubbles starting to form on the surface of the copper, and you can actually see the color changing on the inside there. And this is a result of hydrogen, which is coming off as a gas. Now, there we go. I'm starting to see some hydrogen bubbles forming on the surface of my copper. I can see evidence of my electrochemical reaction taking place. So the copper over here is being coated in a layer of hydrogen bubbles. Now, on the other side, I've got some zinc, which is being eaten up. And I can actually see there's some fresh zinc, which is coming off the surface here. I don't want to get too close to this stuff because it is sulfuric acid. Now, you might say, how does this relate to the thing which is inside my cell phone or my torch? Guys, this is exactly the same as the cell which I've got over here. What I've got over here is the plus N, which is this tiny little extra heightened piece of metal on the top here. That is the positive point on this. And I've got a negative point on this. What I'm going to do is I'm going to turn this back onto voltage measurement and plug that in for the voltage. And we're going to measure it exactly the same way we would the cell. So I've got plus on the one side. I can see that this is measuring an EMF of 1,539 volts. Going back to our other original cell, I can see that the voltage is around about 1 volt, if I round that off. Now, I'm hoping that you guys managed to calculate or at least predict something close to this voltage. Let's go back to the board and let's see if we can calculate the voltage using our standard reduction potentials table. So guys, come with me. What we're going to be doing is we're going to be using that table and we're going to try and figure out what these numbers actually meant on the right-hand side. So I'm going to take these numbers and I'm going to try C, and we're going to try and find out where this voltage actually came from. So I'm not entirely sure yet, but I think it's got something to do with these numbers over here. I'm going to be dealing with the numbers on the right-hand side. These are called my standard reduction potentials. Now, you'll notice that these standard reduction potentials only take place under standard conditions. Okay, now what does that actually mean? Well, standard conditions for a solution are 25 degrees and 1 atmosphere of pressure. Sorry, that's 25 degrees Celsius, not Fahrenheit or Kelvin. Okay, so 25 degrees Celsius, 1 atmosphere of pressure, and 1 mole per decimeter concentration. Now, my acid is slightly more concentrated than that. I did that on purpose to see what it would do to the voltage. So let's try and calculate it from here. Which reaction was oxidation? Which one was reduction? My zinc over here, I can see, is losing electrons. Remember, oxidation is loss. Reduction is gain. That spells out oil rig. So this, my zinc, turned into a positive ion by losing electrons. How do I know that electrons were lost? I write them on the right-hand side of my table. So that is oxidation, and that is my oxidation half. What about my reduction half? I can see electrons going into my reaction. That means that hydrogen was reduced. Now, why am I worried about reduction and oxidation? Well, let me tell you the reason. Zinc is going to be losing these 2 electrons and giving them to hydrogen. That's why we saw the bubbles forming on the copper. Copper did not participate in this reaction. That means that copper was a spectator species, did not participate. Now, what I'm going to do now is I'm going to try and calculate the potential that I should be getting out of the cell. So under standard conditions, the equation goes like this, that the E0 cell is equal to the electrode potential at the cathode minus electrode potential at the anode. So let's do this. Which one was the cathode and which one was the anode? Now there's an easy way to tell. Oxidation happens at the anode. How do I know that? Well, A and O are both vowels, and that's one of the ways that I can remember this. Or I can remember that I like red cats. So reduction happens at the cathode. So I can remember red cat is one of the ways to do this. So reduction happens at the cathode. So we're going to take the numbers for hydrogen, which is 0,00 volts. Okay, that is the standard against which everything else is measured. Minus from that, a negative voltage of 0.76 volts. Something interesting is going to happen. The reason that I put this inside brackets is to make sure that I pay attention to my signs. And that's going to give me a positive potential of 0.76 volts. Guys, I'm sure that you agree that the voltage which I got was significantly higher. So what does that mean about concentration of my electrolyte and the voltage produced? Over here, I can see that my standard potential reaction should give me 0.76 volts. But I got significantly higher than that. What does that mean? Well, guys, that means that I'm getting a higher voltage from a higher concentration. I hope that you can see that. Okay, now let's formalize this. Let's start taking a look at the pieces of an electrochemical cell, which makes up something that I get some power from. Okay, so it says the parts of the cell are the anode, the cathode, the electrolyte, and the external circuit. Now, I've drawn out for you guys, and I think Looney's actually already posted up a whole bunch of stuff on the page. And guys, this picture's in the notes, so you can make some notes over there. I've given these two different colors for a reason. Zinc, as we saw, was a slightly grayish color. So there we go. We got zinc on that side, and we had copper on that side. Okay. Now, I've got a voltmeter measuring my voltage, and that is my external circuit. So that's pretty easy to spot. But what are all these other pieces? Now, I started to see that there were some metals which did some things. Zinc was a place where oxidation took place. So zinc becomes my anode. What about the copper? The copper is where reduction of the hydrogen took place. So that becomes my cathode. So remember, red cat, reduction at the cathode. Now there's something else which I'd like to put on this diagram. I'd like to assign plus and minus. Now I'm going to ask you, beg, please, don't try and memorize these, because it changes according to whether or not you've got a galvanic or an electrolytic cell. You guys have to understand. Guys, you're going to have to do the hard work and try and figure out what's going on here. Okay, so what I'm going to say to you now is that my anode over here is where zinc turned into zinc ions by producing electrons. So these electrons started to build up on this electrode and wanted to go to the other side. The only way for electrons to move, and this is the interesting thing, the only way that electrons can move from one electrode to the other is to move through the external circuit. Guys, this is my negative electrode. Your negative electrode is not always your anode, guys, so you please don't memorize that. That's not how this works. The anode is where oxidation takes place, and that just means that electrons built up on this one. For electrolytic cells, it's the other way round. Okay, so my electrons are now moving around to the other side where they're needed. They're desperately wanted by my hydrogen. So they're going to go inside here. The reason that they move here is because there is a lack of electrons, and that makes that my positive cathode in this case. But again, it's not positive because it's a cathode. It is just positive because it is lacking electrons, because those electrons are being used up by the hydrogen. Okay, so now that we've labeled the parts of this, there's one final thing. There's a piece that I have not labeled, and it's called the electrolyte. Now, guys, you might have heard of electrolytes before, especially when you start to think of like sports drinks, or you start to think about long-distance running or training. Electrolytes are very important for your body's functioning, because my brain is the biggest circuit I know. There's wires going around inside my head. Well, some of us have more wires than others, but now, all of us have to use electrolytes. Electrolytes are the ways that conductivity actually takes place. And there's no difference over here. What did I use for my electrolytes over here? I used H+ ions. I used sulfuric acid. So I used the combination of these two. My electrolyte was the sulfuric acid between them. Now that's what's going on inside that liquid. That liquid is usually the electrolyte between the two. So if you wanted a definition for an electrolyte is a conductive fluid between the two electrodes. So an electrolyte is a conductive ionic liquid. So it's filled up with iron, so it's nice and conductive, and it conducts between these two electrodes. Okay, so now a lot of you are saying, Phil, this is a lot of information, so let's just slow it down, go through this again before we go to the ad break. Okay, we connected our voltmeter. That was the external circuit. That's what the wires are actually stuck to. Then I stuck in my zinc and my copper. Now my zinc underwent some oxidation. It turned into zinc 2+ plus 2 electrons. It lost those electrons. Where did the electrons go? Well, guys, the electrons always go into the wire if they're being made. And then they went around through my voltmeter and then down to the other side. and there they did reduction of the hydrogen, and we actually saw those beautiful bubbles. And that's what resulted in my copper becoming the cathode. Okay, and just finally, guys, the electrolyte is the conductive liquid between the two. I hope that you can see that all of these parts actually fit inside a cell. Now, here's the really confusing thing. Guys, when you take a look at one of these, I don't see any of these things. I don't see a beaker. I don't see electrodes. The only thing which you see is the outside circuit. I see the bits of metal on the outside. So what we're going to do is when I come back is I'm going to show you a picture of what happens when you cut one of these open. Now, guys, please don't do this. Okay, I once did it a long time ago, and it's really easy to cut and poison yourself. There's a lot of dangerous chemicals inside here, so please never open one of these. Okay, now we're actually going to show you what happens when you cut one of these open, and you can actually see the inside of one of these. Then what I'm going to show you is something really cool. We're going to make our very own battery. Not just one over there that discharges and makes some hydrogen bubbles, but guys, we're actually going to make our own battery that can even recharge. Guys, I think it's time for a short ad break. What do you think, Looney?
Yes, you can.
How's the page looking?
I just want to read one comment here from
Awesome.
a mindsetter. Telly Bubbles Courage Baumela says, "Hello, my darling Looney. Hope you're doing great. I'm enjoying the show here with my sister Mataga. Shout out to my dearest Phil there. Mega love to you and all the mindsetters." Thank you so much for that very cute message. Shout out to you too. You are an awesome mindsetter. And then we have some answers. Negative 0.76 volts of electricity.
Almost there, guys. You got the correct voltage, except there's one difference. I can tell you exactly what went wrong over there. It was the brackets, guys.
Right.
Please substitute using your brackets, because that means that my positive voltage has got to come out there.
Okay.
Now, that positive voltage means that I can actually use my battery or my cell to do some useful work.
Right.
Positive voltage is good for my batteries.
Okay, cool. So Vashni, Naidu, make sure you just check your signs there, but you almost got it right, so well done to you. Mindsetters, we are going to take a very short break, so we will be back straight after this. Welcome back, Mindsetters, from that very short break. Phil, we do have a couple of questions, if I can just
Yeah, let's go
ask
for
you
it.
quickly. Okay, Nzova is asking, may I please ask our teacher to explain the terms dry cell and primary cell?
Oh, I'm so glad that he's asked that, because that's exactly what we're going to be doing here.
Okay.
Okay, well, guys, I'm busy holding here a dry cell. You'll notice that there's another cell over here that I've made, and this definitely isn't dry. I can see that this is called a wet cell because the electrolyte is a liquid. Now, inside a dry cell, I've actually got a paste. It's almost solid. It's that dry. And this is the reason that that's actually called a dry cell. So these things which you put inside your remotes or inside your torches, this is called a dry cell. Now, the other question which is asked, a primary cell or a secondary cell. Now, guys, this type of cell can only be used once. Once it's finished, I've got to throw it away. Now, guys, when you are throwing away your cells, please make sure that you're recycling them, because sometimes there's toxic metals on the inside. And, guys, if you're wondering how to recycle them, just take them along in your mom's purse or whatever. There's a bag, and there's usually drop-offs at shopping centers. I think especially Pick n Pay's got some, Woolworths has got some. Guys, there's recycling centers over there. Now, these, once they're flat, I can't use them again, and that's obviously a problem. Now, to counteract that, I've created my very own secondary cell, and that leads us really nicely into our experiment. But before we go on, is there another question?
Yes, Mokosi is asking, what happens to the electrolyte, cathode, anode when the battery is dead?
Oh, okay. What's actually happening on the inside here? Now, there's a bit of a problem. I can't actually see what's going on inside here. But for this cell, this is a primary cell, what you'll actually notice is that the zinc actually gets oxidized and eaten away. So the electrolyte is going to change which ions it's got inside it, and usually the electrolyte decreases in concentration as time passes. Okay. So that's a really good question as well. I'm glad to see these guys are asking.
Okay. One more question from Bobosia Bonga. He's asking, explain please that casing of the battery corroded by the acid inside. So maybe he's asking what happens to
All right. So now what you're seeing on the outside here is actually a plastic label.
Okay.
Now if you look at the ends, you'll actually notice that there's metal on the inside here, and that is the metal casing. Now inside that casing there's another casing as well, which is made up of zinc metal, and this is zinc metal. Now that gets oxidized or corroded. So as a battery gives out its energy, this actually gets eaten away. It's actually going to get oxidized from the inside. Sometimes the oxidation occurs only in one place, and you actually see the electrolyte leaking out, and you get that white fuzziness, which leaks out into the battery compartment of your appliance or your remote or whatever might be the case. If you see that white stuff, guys, please don't touch it. That is usually ammonium chloride or it's potassium hydroxide if you're really unlucky. And guys, that stuff, it really can hurt you. It's very corrosive and dangerous. So if you see white stuff leaking out of a battery, okay, wash it off your hands and then put it into a packet and send it to one of those recycling centers. Really awesome questions, grade 12s. Okay, now we've talked about a dry primary cell. Now what I'm going to do is I'm going to introduce you to the type of cell which is inside every car, every truck which has got a battery, and hopefully that's everyone. Now what I've got here is two lead-based electrodes. In between them, I have got a sulfuric acid electrolyte. So what I've actually done is I've connected positive to the one side and negative to the other side, and I'm going to allow the current to flow. What I'm going to do is, instead of doing a galvanic reaction where I get energy out, I'm going to charge my battery the same way that you would charge your cell phone at home. I'm going to use my power supply over here. You'll see a green light over there when it's charging, and I'll actually see bubbles of hydrogen and oxygen on the inside of this. For this reason, you should never charge a lead acid battery indoors because it makes explosive gases. So watch what's going to happen. I'm going to show you what happens when it charges. You can actually see the bubbles forming at these two electrodes. I hope that you can see that on the camera there. I'm fairly sure that you can because there's really nice bubbles occurring over here. I've got a negative electrode where there's hydrogen forming, and I've got a positive electrode where oxygen is forming. What that's actually doing is charging up my cell. Now the way that it does that is it changes the lead into lead dioxide. Now before we get too wrapped up in the chemistry, I want to show you why I'm doing this. This is giving charge into my cell. At the moment, it is an electrolytic cell. Electrolytic cells take electrical energy and change it into chemical energy. Now here's the part which I really love. I want to see if there's energy stored inside my battery. Well, this isn't actually a battery, guys. I hope you corrected me. This is actually a cell. So now I'm going to disconnect my power supply. So you can see that my power supply is now well away from here. Now the first thing which I'm going to do is I'm going to test the voltage. So let's do exactly that. Let's bring my voltmeter over here. Let's stand it where you can see it, and let's test the voltage. Okay? Now hopefully there's some voltage inside my battery over there. Ah, very nice. I can actually see that there's almost 2 volts stored inside the cell. It's a very good demonstration of what a lead acid battery should do. Lead acid batteries are 2 volts per cell. Now over here I can actually see that there's 2 volts over there. But now you say, okay, well Phil, there's just numbers on a screen. I can't actually see that there's energy stored inside the cell. So what I'm going to do is, to prove to you that there's energy stored inside, is I'm going to put some of those electrons to work. I'm going to collect I've got here a tiny little torch cell, and this torch cell is designed to shine when I apply a charge over it. So watch very carefully, because the energy is going to disappear quite quickly. But as soon as I connect it to this cell, and you can see that there's no other wires connected to it, as soon as I connect it there, I can actually see that this torch bulb has lit up. I can actually see that there's energy stored inside there. So as I disconnect, I can see that the torch cell goes off. Reconnect, I can actually see that there's energy stored on the plates of this cell. I can see that my energy is flowing out of here from the negative all the way around, and we can see that our energy is now finished. You can see that the energy doesn't last forever. So I can recharge it if I like. So if I want to make it electrolytic, I can charge it again, and this is just like recharging your cell phone. Okay, so there we go. Let's switch it on and let's charge my cell phone. So this is my cell phone cell, and what you can see is that I can store energy again. So I'm putting energy in now, and let's see if the energy is stored there again. Absolutely. When I connect that again, and we can see our light bulb is glowing nice and brightly over there. So you can actually see that our light bulb has now been restored. We've stored energy inside the cell. I particularly like this because it's a very own battery that we can make, and this is exactly the type of cell that you'd find inside a car or inside a truck or inside almost any installation which needs to store up some charge. Very, very simple. This battery was, this type of battery or cell was invented over 150 years ago, and it's still in use today. We don't really have many better options because it's a really nice, cheap way of storing electricity. So guys, let's take a look at what actually happens on the inside of these cells. So I want you to walk with me a section, and we're going to see what actually goes on inside these. Remember when I told you guys, please don't cut open a dry cell? I'm going to show you exactly why. Dry cells are primary cells, and they can only operate once. So over here, we're going to start talking about these terms of primary and secondary. Primary cells can operate once and are only galvanic. What does that mean? Once the reaction is finished, they can't give out their energy anymore. So I've got a diagram over here, and I think Looney's already posted it up to the page, of what a cell actually looks like. I've got a dry cell over here which has been cut open. Now there's some pieces over here which I'm particularly interested in. The zinc case is one of them, and that's the part that sometimes leaks, because the zinc case is the anode. That's where electrons are made, and that is why the bottom plate is negative. You can see that electrons gather over there. We even tested this. Now inside, this is the interesting part. This is why it's called a dry cell. It's a jelly or a paste. It's not a liquid like that wet cell that I showed you. And that is the business part of the cell. This is the reason that I can take one of these cells, put it in my pocket, put it in my torch, and it's not a problem. Now on the other side, you can see another electrode called a carbon rod. There's a reason that I use carbon. This particular type of carbon is called graphite. I use it for these two reasons. Carbon, or graphite at least, is very non-reactive. It is said to be inert. And the other reason is because it is also one of the few non-metals which can conduct electricity. So it doesn't react and it can conduct electricity. And here we go. This is one of the ways that they increase the surface area of it. They powder some carbon and mix it with some of the reactants, some of the electrolyte. Okay, now here's the difference from the secondary cells. Now I showed you some primary cells. I showed you the zinc copper cell, and I showed you the Duracell, that tiny little D cell. That was a primary cell. Those I can only use once. Once I use them, the electrolyte usually gets used up and one of the electrodes is falling apart and I can't use it anymore. Secondary cells. Now this is where, I mean, if you can solve the problem of secondary cells, guys, there's a Nobel Prize waiting for you, because the world is waiting for a really good way to store electricity. I told you that the type of secondary cell that I made was invented over 150 years ago. Now the secondary cells, this is what makes them so special. They can recharge. I put charge in, the charge can come back out, and that's the amazing thing. Now, I'm sure you've all experienced the frustration of a cell phone battery dying long before you were ready for it. Or, yeah, I can hear Looney's going, yes, 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 my laptop, my cell phone, whatever, it all dies eventually. The problem is that these secondary cells don't hold their charge long enough, and they don't store enough energy. Now, here's the really special thing. These cells can be both electrolytic and galvanic. That's the really special thing. They can do two opposite processes. I can take electrical energy from the charger, put it into chemical energy, and store it. Then I can carry it with me and give out again into electrical energy using a galvanic reaction once more. Okay, so guys, I hope that you can actually see that this is one of the really, really special ways of doing things. Now, before we get too carried away, I want to show you two very special formulae. You've seen these formulae before. Now these formulae are very, very useful for calculating two things. Q is equal to IT. This is something that we've seen before. Q is equal to IT is an equation which is used to calculate charge. Now over here, we're going to use it to calculate the cell capacity. Okay, over here I can see there's a tiny little spelling error. I'm also going to calculate the cell energy. I got so excited we left out an R. Okay, what about the current? Okay, the current is the same. Now here's where cell capacity differs. The time which is used is no longer in seconds. The current in amps, the time in hours gives us a unit of amp hours. That's the difference. Now what about the energy which is stored inside the cells? Well, if I use volts like I usually do, but instead of using Q in coulombs, I use amp hours, I get my cell energy in a new format, and that is in watt hours. Okay, guys, I had a little worked example, but I thought it might actually be better to skip right forward to some exam-style questions, because this exam-style question, I really, really love this. This was adapted from the finals last year, the Department of Education Paper 1, question 10. So over here, the following half reactions take place when a non-rechargeable alkaline cell. So guys, non-rechargeable alkaline cell, that should tell you something immediately. I hope you know what that means. Okay, we've got two half reactions happening over here. I've got one which produces electrons over there. So I've got production of electrons over there, and I've got the consumption of electrons. Electrons are being taken in over there. Now it says, write down the general name used for non-rechargeable cells. I wonder how carefully you guys have been listening. Non-rechargeable cells. Well, non-rechargeable cells are called, and somebody asked it, primary cells. Primary cells are the name for non-rechargeable cells. These are the types of cells which are most common. But remember, guys, the environmental problem with primary cells is I have to throw them away all the time. And sometimes they've got toxic chemicals, like mercury inside them. And sometimes it would actually be really nice to be able to use them many times before throwing them away. Because remember, all the energy and the effort and the time that it took to make that cell is very valuable. Guys, we are running out of resources. We can't be throwing away valuable metals. Okay, now this one I really like. It says, which one of the above equations, 1 or 2, represents a half reaction that takes place at the cathode? Now it says, give a reason for your answer. Okay, guys, remember what I said about the cathode? Something happens at the cathode. Now you're thinking, what did Phil say about the cathode? Cathode starts with cat, and that is where reduction takes place. So reduction is taking place. And now I'm looking for a reaction which is reducing some material. Now looking at my reaction over there, which one of these reactions? Oh, wait a minute, I can see electrons on the left-hand side over there. That is reduction taking place there, guys. Reduction is when electrons are on the left, I'm taking them in and adding them onto something. So that means that reaction number 2. My reasoning is because reduction is occurring. And that is the reason. Okay, but guys, we're not done yet. I want to start dealing with some of the really interesting calculations taking place in this one. Okay, so there I've got my reactions again. Now it says, give a reason why the cell dies after a while. Okay, now it's really unusual to use a word like dies. You don't have a battery which is going, busy dying on you. Okay, even though you might feel like this when your cell phone's busy dying on you. Okay, why do I say that the cell dies during use? Now there's many reasons that we can say that a cell might eventually stop giving out its charge. And the usual reason is that it runs out of chemicals to react. It runs out of electrolytes, or one of the electrodes runs out. And that's one of the reasons that my cell might actually die, is because we run out of reactants. And it's usually the electrolyte. And this is one of the reasons that sometimes that the car won't start in the morning. It's because we've run out of electrolytes. Now, every battery's got different electrolytes inside it. The car battery's got sulfuric acid. That's not the sort of electrolytes you want inside you. Okay, now here's the real business end of this question. It says that the EMF of the alkaline cell is 1.5 volts. The maximum amount of work that can be done by this type of cell, oh, wait a minute, that's in joules, guys. 3 times 10 to the 4 joules. That is 30 kilojoules or 30,000 joules. Okay, now we've got to calculate the cell's capacity in amp hours. Oof. How do I change from joules into amp hours? Okay, now one of the things that I've got to remember for myself is that joules, how did I get to joules in terms of energy? Well, I know that work is equal to V times Q. If I want joules, I must put in volts, and then I must put in charge in coulombs. Okay, but the problem is that I didn't put it in coulombs. I put it in amp hours. So what am I going to do here? All right, well, one of the things that I can do is I can start playing around with my energy over there. I've actually got W, it's just in the wrong units. Okay, so now what I'm going to do is I'm going to start changing things into the correct units. Okay, so now we've got several approaches here. I've got energy, which is in joules, which is my work which is being done. I've got a voltage. That means that I can get Q. Ah, wait a minute, but if I use joules, I'll get coulombs, guys. Okay, so Q can be calculated, and this is what I'm after. So if W is equal to V times Q, Q is equal to W over V. Now that's really interesting. That's really not too difficult to do. So W over V is the way that I'm actually going to calculate this. So now to calculate the cell's capacity in amp hours, first I'm going to calculate the capacity in coulombs and change it up. So my Q over there, let's actually do this right down at the bottom. I'm not sure that we're going to get time to do all of this. So my Q is equal to W over voltage. So over there, so we're going to look for our work, which is 3 times 10 to the power 4. And then my voltage of 1,5. And what we're going to find is that we're actually going to divide this up. So if you divide that up by 1,5, what you're going to find, how do we do that? Okay, let's just get our calculator quickly. All right, unfortunately, I don't have my answers there with me. All right, let's just get our calculator quickly, my wonderful Casio calculator. All right, now what we need to do inside there is we still need to change our answer when it comes back through there. Just remember that my answer is still in the incorrect units, and we are running out of time, I'm afraid. So we're going to get an answer over there, but that's not going to be in the correct units. What we still need to do is to take our answer from that and change it. What we'll get is an answer which is in coulombs, but I want it in amp hours. Now, I want to leave it as a little bit of a challenge, but I'm going to give you a little bit of a hint. There's another way of doing coulombs. Coulombs is measured in amp seconds. So amp seconds actually gives me coulombs. How do I get from there to amp hours? What I'm going to do is ask Looney if there's any questions while I quickly grab my calculator, and then we're going to start playing around with some of these calculations. Okay. Looney, how's it looking on the page there?
Musa is asking if reduction is recurring, what about oxidation?
Oxidation absolutely is recurring. So oxidation and reduction are happening. Reduction at the cathode, oxidation at the anode. Okay. Really nice question.
And then another one from Emmanuel. What is the difference between electrolyte and What is the difference between electrolyte and electrolysis?
Oh, between an electrolyte and electrolysis. Electrolysis is a process where you run electricity through an ionic liquid. An electrolyte is the ionic liquid itself. Okay. Okay, cool. Let's just quickly do this calculation, and let's put everyone out of their misery. So what I'm going to do is I'm going to take, I think, 3. Let's just take that there. Okay, so 3, we're struggling there. Okay, 3 times 10 to the power 4, so there's my joules, divided by 1.5. There we go. So that's 20,000 coulombs, but now to change into amp hours, guys, the way to change from seconds to hours is to divide by 3,600. There we go. And there's our answer in amp hours, which is 5,56. So there we go. My final answer is 5,56 amp hours from 20,000 coulombs. Unfortunately, we don't have any more time, guys. Looney, it's been amazing.
All right. Thank you so much to Phil, and thank you to Macmillan for bringing us a great show. Thank you, Mindsetters, for tuning in, and until next time, we'll see you then.